Hi, this is the second video made for the class Nonlinear Modeling of Reinforced Concrete taught by Dr. Guner here at the University of Toledo. In this second video, I will continue from where we left on the first video. So if you didn't watch that yet, I recommend you to pause this video right here and watch the first part where we model this simple beam structure present in this handout right here. And we got to the conclusion that the response calculated by SAP2000 using the shear hinges that it calculates by default gives a pretty conservative result, which is really off from the values we calculated by hand using the ACI318 code. So in the last video we saw that the shear hinges dictates the response of this beam, which indicates that this beam has a shear critical behavior. So to try and make this beam behave more realistically, we will edit these shear hinges in this video in order to try to simulate more accurately the shear capacity of this element at these specific sections. For this, we will be using the software called Response2000 developed by Professor Benson Collins at the University of Toronto. Response 2000 basically performs a sectional analysis of a reinforced concrete cross-section that the user defines. However, differently from hand calculation sectional analysis that we do based on reinforced concrete codes such as ACI 318 or AASHTO, Response 2000 take into consideration the nonlinear behavior of both the steel and the concrete in the cross-section. In this figure, I have the assumptions we normally do when we calculate sectional analysis moment capacity of reinforced concrete cross sections. So we normally assume that the steel has a maximum capacity based on its yield stress, and we assume also a rectangular concrete distribution with 0.85 f prime of c as the ultimate capacity in the cross section. So Response 2000 won't do these simplifications and will account for the nonlinear response of both materials to calculate a more realistically sectional capacity of the beam we want. In addition to the moment capacity of the cross section, Response 2000 will also calculate a shear capacity of the cross section based on the modified compression field theory, which we will specifically use in this video since our focus here is the shear hinges of our model. So I will go into step by step on how to include our cross section in this software and get the response we need to implement it in SAP 2000. So the first thing you want to do is come here to define, quick define. And here Response 2000 lets you give a name for your analysis. I'll just call this video 2. And here it asks us for some basic material properties that will be present in our cross section. So going back to our handout, we see that our reinforced concrete strength is 22.6. Our transverse reinforcement D5 has a yield stress of 600. And for the longitudinal reinforcement yield stress, Response 2000 asks us for only one number, but we have 3 different rebars. Right now, that's not very important since we will edit those rebars later on. So let's just give the yield strength of the M30, for example, which is 436. Since we won't have any pre-stressed steel rebars on our cross section, I'll select none here and click next. Here we can select the type of cross section we will have. In our case is rectangle. And I'll input 305, 552 and click next. In this next window, Response 2000 asks us the number of bars we have in the bottom layer, in the top layer, and the number of bars in the bottom layer. So in our top layer, we have 3 bars. And here we can put what types of bar it is. In our case is 10M. If you want, you can also specify the bar by its area and not by its name by clicking on this box right here. In the bottom layer, we have 2 layers of 2 bars. Since, like I said, we will edit this later on, I'm just include the 30M bars and click next. Now, Response 2000 wants us to inform him about the transverse reinforcement. First, the stirrup type, We can choose from single leg, open stirrup, closed stirrup, hoop, T-headed, single leg, and interlocking hoops. In our case, we have a closed stirrup. Our bar is a D5. The spacing of the transverse reinforcement is 210 millimeters. And for the clear cover, let's go back to our handout. And from the previous video, we know that the distance from the bottom of our cross section to the center of our M30 bars is 64 millimeters. Our clear cover is the distance from the bottom of the cross section to the bottom of the shear reinforcement bar. Also, on the top right here, the distance from the top of the cross section to the center line of the top reinforcement is 50 millimeters. So the clear cover on the top is slightly less than the clear cover on the bottom. Here in response to 1000, let's input one of them. I'll put 42.65, and after we finish here, I will edit this so we have the correct clear covers on the top and the bottom. We don't have any pre-stressed rebar, so I won't input anything in the bottom tendons, and I'll click finish. And here response 2000 shows us the cross section quickly defined for us based on the information we provided. Here on the lower left side of the screen, you can see the concrete stress strain response and the reinforcement stress strain response that it will consider in its sectional analysis and shear calculations. You can also see some geometric properties and some other useful informations. So looking at the cross-section representation here at response 2000, we see that our second bottom reinforcement layer is missing. So to include that, since we have a different material for all the longitudinal reinforcement, let's first create the materials for the second layer. So let's come to define, material properties, rebar details, and here we can see that response 2000 already created two reinforcement materials, one for the shear reinforcement, the stirrups, and one for all the longitudinal rebars. So right now we have the same material for the 30M and the 10M bars. We want to have different materials for the 10M, the 30M, and the 25M that will come here later on. So let's rename this longitudinal here to 30M. Click on modify. Click yes on this message. And here we can also change some specific information of this rebar if we want to fit it more exactly to what we had in the experiment or what was seen in the laboratory. So in our case, we have those kind of informations from our handout. So for our M30, for example, we have that the ultimate stress this bar can handle is 700 MPa and the module of elasticity is 200,000. So here we can come and edit this 700 MPa and the elastic module is already correct. The E-strain hardening strain value at which the stress strain response of the reinforcement starts to go into strain hardening phase and the ultimate strain at the peak, we don't have those values from our handout, so let's leave the default values used by response 2000. So I'll do this for the other two reinforcements and come back to continue this problem. Alright, so I have updated all the values from the reinforcement materials from our handout and created the additional ones we needed. So let's click OK. And now let's include our second bottom layer reinforcement. Again, I'll come to define, and this time I'll come to longitudinal reinforcement. And in here we also see this response 2000 create both the bottom and the top reinforcement layer. So I'll start renaming this to bottom 2 and adding it. So now we have 3 layers. Our third layer, it will be a 25M, also 2 bars. And the distance from the bottom is 2 times 64 from our handout, which is 128. And here on the bottom we can select the material property we are gonna use for this rebar. So select 25M, click on modify so it updates. And now that we've done that, I'll come back to the bottom one, check that the rebar type is the correct material type. I'll go to the top, 10M, and I'll change this to a 10M material type that I just created. I'll click modify so it updates. And also here I'm gonna change the distance from the bottom, because when we quickly define this cross section we had to pick one clear cover value to define for the entire cross section. Here I can manually change the position of the rebar, which was previously automatically calculated by response 2000 based on the value of the clear cover. So it is asking for the distance from the bottom. We know that the entire depth of this cross section is 552 and the distance to the center of the top bar is 50, which leaves us with a distance from the bottom with 502. I'll click on modify and click OK. And once I click OK, you should see the cross section updates to include the layers I just created and the distance I just specified for the top reinforcement. So I'll click OK, and you can see the second layer and that the top layer moved a little bit closer to the top face of this cross section and kind of overlapped with the shear reinforcement. So to edit the shear reinforcement, we come to define again, and this time we choose transverse reinforcement. Here we only have one stirrup, so I won't create another one. I'll just edit the ones we have here. So the spacing is 210 like we said before. The bar designation is still D5. Here the distance from the top to the top and distance to the bottom is basically based on our clear cover, which we couldn't differentiate between top and bottom before, but here we can. So I'll update this value to consider the clear cover from the top layer of our longitudinal reinforcement. And the distance to the bottom should be okay since we picked the bottom one when we first defined this cross section. The bar type is still closed stirrup and the rebar type is also the transverse reinforcement. I'll click on modify so it updates and click OK. And now we see that our shear reinforcement moved a little bit up and it doesn't overlap with our top longitudinal bar layer as it was before. So we have updated all the information from our longitudinal and transverse reinforcement. Now if we wanted to update the information of our concrete, we could also come to define material properties, and here on the concrete we would click on detail F prime of C, and here we can manually update some information in our concrete such as the tension strength, the peak strain, aggregate size, tension stiffness factor, some theories for base curve, compression softening, and tension stiffening if we wanted to. In our handout, in addition to our strength of the concrete, we have our peak strain, our modulus of elasticity, and our tension stress based on a split cylinder test. So if we want to, we can include these two values here into response 2000 since there's no field for elastic modulus. So here I include the tension strength at 2.37 and the peak strain as 1.6. Click on modify so it updates and click OK. Alright, so now we can actually start to get some results so we can use in our SAP2000 shear hinge definition. So the first thing we need to do here is to define at which load condition this cross section will be subjected to, because this will be important to calculate both the moment rotation relationship as well as the shear force and shear displacement that this section will be subjected to. Because since this software accounts for the modified compression field theory, both the shear and the moment are considered together and they influence in one another based on their relative magnitudes. So to do that, we can come here to loads and set the sectional loads. And response 2000 will ask us the axial load, the moment, and the shear load. And we have a column for constant and a column for increment. So here what response 2000 will do is, like a pushover analysis, it will keep increasing the moment, the shear, and the axial load and calculate the response of this cross section as this loads increases. And in the end, it will plot us a moment rotation curve or a shear force versus shear displacement curve as both of these effect gets increased. So in this window here is where we define by how much each of these effects will increase respectively to one another in each iteration of the response 2000. So for example, right here as default, we have everything 0 on the left side, so the constant part is 0. So there's no load that will be constant throughout the entire analysis of the response 2000. And response 2000 will increment 1 kilonewton meters of moment only in this cross section every time until the cross section fails, and it can show us a full moment rotation relationship response for this cross section. So right here, if we leave it as it is, response 2000 will not include any type of shear load in this cross section, and therefore we won't be able to get the shear response of this cross section. It will only perform a moment analysis since the moment is the only acting load on this structure. Since this can be seen as an increment value, in the increment column right here, we should put the relative values of the moment, shear, and axial if all of these three effects are going to be increased in the analysis. So here in our example with a simply supported beam with a point load in the middle, we know that our shear diagram and our moment diagram will look like this. And we can also see that at the sections where the shear hinges are located, the shear value and the moment values are different, but they keep the same ratio to one another as the load increases. So here in response 2000, we will use the ratio between shear and moment magnitudes to specify how the increments should be. So here on our simply supported beam, I will do a simple calculation imagining that we have a 1 kilonewton point load in the middle. So I know that the shear diagram on both sides of this beam will be half kilonewton and half kilonewton. The moment on each hinge, however, will vary linearly from the supports to the midspan of this beam. Therefore, the moment to shear ratio will differ for each hinge, whether they are closer to the support or closer to the midsection of this beam. So here in our shear hinge that is closer to the support, we have a shear to moment ratio of 2.19, which means that for each 1 kilonewton meter that section increases in moment, the shear increases in 2.19 kilonewton. So when we input these values here, on each iteration, response 2000 will add the moment in this cross section by 1 kilonewton meter and its shear in 2.19 kilonewtons. Since this is a beam analysis, our axial load won't get increased, nor will have a constant value at the beginning. If we were modeling a column where we want to study a pushover axial load, we would include the axial load here on the increment. Or if we had a already axially or if we had an already axially loaded column and wanted to study the increase in the moment in that column, we would increase the moment here in the increment column and set a constant value for the axial load of that column. Axial load can either increase or decrease the moment and shear capacity of a beam based on if it's a compression load or a tension load. For compression loads, we should input the negative sign in front of our specified load, and for tension, we should include the positive sign. So since I already have everything set up for our first shear hinge, I'll go ahead and click OK here. Come on the Solve menu and run the sectional response of this cross section. And here you can see that Response 2000 calculated a lot of information on our cross section, such as the principal tensile stress, the shear on the cracks, the shear strain, and the shear stress based on the height of our cross section. You can also see the compressive part of our cross section, the tension part of our cross section, the crack diagram. So there's a lot of useful information depending for what kind of application we want to use this for. Here on the left side, we can see both moment curvature graph and the shear force versus shear strain chart. In our case, since our SAP2000 from our previous video had a shear critical behavior where the shear hinges in SAP2000 basically control the entire behavior of our beam, we will only focus on changing the shear hinging by making it follow this curve right here in response to 1000. So to grab this curve, I'm gonna right click here and click on view data. And here response to 1000 shows us the same values as a list where we can copy it and paste it on Excel if we want to do any kind of manipulation with it. So if we come back to SAP2000, come on define section property, hinge properties, click on modify and show property like we did in the last video. So we come back to this window where we have the shear stress and strain response of our shear hinge. And we saw in the previous video that this response follows a predefined stress strain response from many codes, and I showed you in the previous video in FEMA 365 code. So we are going to edit these points right here to make it match the one we found, the response we found for this section in response to 1000. So if you remember from the previous video, we just defined one shear hinge and applied it for both locations in our beam. So first thing we need to do is add a copy of this property, call it shear hinge mid, click OK, and change the name of this one to shear hinge support. Okay, so since we calculated it for the support in response to 1000, let's modify this one. And here we can see that the points on the stress strain diagram here comes from this table. And here in this table we can see that the values of stress and strain are normalized to these SF values. And these SF values are defined here on the scaling for stress and strain. So the values we should input here to customize our stress strain curve should be normalized to the values we input here. So these normalizing stress and strain factors are the yield stress and the yield strain of our cross section. These values represent in this standardized stress strain response the values at which the shear hinge starts to deflect a lot, which we call it as the yielding of the hinge. That's why it's called yield stress and yield strain. So here we should pay attention that SAP2000 requires us to input the stress and strain based on our set of units right here. So in our case, MPa and millimeter per millimeter. And response 2000 give us a shear strain in millimeter per meter versus shear force response. So to transform this to the shear strain and shear stress required to input in SAP2000, I'm gonna simply divide this by the area, which in this case is width times effective depth instead of width times height. Also, because this is kilonewton, I'm gonna multiply by 1000. And in here, to get millimeter per millimeter, I would divide this by 1000 since this is millimeter by meter. However, because we specified that our shear hinge length is 685.5, instead I'm gonna divide this by 685.5, and now I have the shear strain versus the shear stress to input in our SAP2000. Alright, so here in SAP2000 we have to specify the points at which the normalization will occur for our stress and strain curve. SAP2000 refers it as yield stress, and we should try to pick up a point where we believe the yielding starts to occur in our section. However, sometimes it might be difficult to actually visualize the point where yielding starts to occur. In reality, it doesn't really matter which point you pick as long as you keep all the points that you're gonna calculate normalized to this point that you decide to pick. In my case, I'm gonna make the origin. In my case, I'll pick this point as it looks like the curve starts to deflect a little bit more. So I'm just gonna make this 149 and 176.151. And this curve is in force and strain, so this point is equivalent to this stress. My second point is gonna be the peak, which is 254, which is equivalent to this. And my last point will be the very last point we got from response 2000, which is this one. So now to normalize everything to my reference point, I'm gonna go and simply divide them by our points. And my very last point, as we can see, SAP2000 has 4 points to be defined, and we only have defined 3 after the origin. So my last point, to simulate this drop right here, I'm gonna give a little bit more displacement or strain than my previous point. So I'm just gonna make this 27, but I'm gonna drop considerably the stress. So I'm gonna make this 25, for example. It can be any number as long as it's considerably low in comparison to the last point. So right here we already have the values to input in our shear hinge in SAP2000. These two will be the values for the normalization, and these will be the values normalized that we will put in our stress strain response. So I'm gonna put these values there on SAP2000. So here I have the curve in SAP2000 with the points that I had calculated in Excel, and we can see that our curve looks a little bit similar to the one we had in response 2000. Right here for point B, where the yielding is considered, SAP 2000 has a default of 0, meaning that no displacement or no deflection occurs until yielding. And you can put it as 1 to get the value that you input as the normalization. However, it is stated in the SAP 2000 manual that no matter what value you put here, SAP 2000 will never consider it and it will always be 0. So you can leave it as 1 or leave it as 0, as it comes as default in SAP 2000. It won't be considered by SAP 2000. Also, we can see that our curve resembles the one we got from response 2000. And since we only have 4 points to define the curve, and these points will be connected by lines, it's good to try to specify the response location where we think it will also look like as our response. So here we can see that the connection with lines doesn't differ a lot from the response we got from response 2000. Before we click OK, here on the bottom we can see again from the previous video the immediate occupancy, life safety, and collapse prevention points, which are defined based on strains that are also normalized to our yield strain. So if I click here to see on our curve, we can't really differentiate them in our curve because these values were calculated based on our previous default calculated hinge parameter, so we can't really see them. But just so we can just so you can see how we can modify it to fit our curve, I'll input a value of, for example, 10, and here you can see that the immediate occupancy point moves slightly after our peak capacity. So in this video, I won't go into details on how to calculate these values for our beam. But if you want to do that, this is how you modify it to show in your... This is how you modify it. So the colors of the hinges change as the beam gets loaded in your situation. In this case, I'm just concerned on comparing the final force displacement response so we can see how this modified shear hinges will help us or not to get a better response. So I won't bother with these values right here. I will click OK, and I will do the same procedure to our shear hinge in the middle, where I'll go back to response 2000 and input the different moment shear ratio that we have for the shear hinge in the middle, get the response from response 2000, go to the Excel and do the same process we did for the support. So here I already went ahead and ran the analysis for this model, and for the result I'm just gonna keep pressing this arrow so we can progress through the steps. So we can see that the shear hinges are the critical ones in this situation, since they already started to change colors, and the moment hinge in the middle still hadn't shown any difference, meaning it didn't even get to the point where it yields. So I'm just gonna keep progressing it, and we can see that the shear hinges at the middle it starts to go into some pretty heavy loading. I'm gonna keep, and now we can see that the moment hinge at the middle started to displace past the yielding point. So we can see a junction between a shear critical behavior and also a flexure behavior here. So we can expect some plateau in our response due to the yielding of the moment hinge. Let's continue. And right here, the shear hinges in the middle fail, and in our response we see a sharp drop in the force displacement response. Before I get the graphs and plot it in Excel to show you the difference like I did in the last video, one thing that I didn't mention is that we can also check the response of the hinges by going to the display, and instead of pressing show plot functions, we can press show hinge results. And here we can select the hinges we want to see, and it will show you the response that the hinge went as the load increased here. So for example, you can click on these items to have a better vision of the response. So I'm just going to click all of them, and you can see that as I increase the steps here, our gray circle represents that shear represents the path that the shear hinge went through as I loaded the beam. And here you can see that the shear that the hinge was being subjected to at the step that I am accounting here. So I'm just gonna keep, and you can see that it follows the path that we specified in our shear hinges until it failed right here. And you can select the what hinge you want to see in this drop down right here. Okay, so now I'm gonna get the response and go back to Excel to show the difference between this new model and the one we modeled in the previous video. So here we are at Excel, and this curve is the displacement based curve that we had on the previous video, already considering the correct moment of inertia of the hour beam. And for the rest of this video, I won't include the force response that we got from the past video. I'm just gonna focus here on the displacement response that I got, and I'm gonna show the one I got using the modify hinge that we did. And as you can see, the difference is quite different, especially in terms of capacity of the beam. With the modify hinges that we implemented, we see that our hinge resists a point load in the middle almost at the same that we calculated by hand using ACI code, for example. As I mentioned in the last video, if the response we get using a finite element is between around 20% more or less than the one we calculated by hand or the one we expected, then we can say that our estimate is accurate enough. However, as you can see in terms of displacement, even with the modify hinge, the displacement is quite different than the one we expected by hand. You might even think that the default hinges of SAP2000 is better in terms of displacement than the modify hinge. However, that's not true, and to illustrate that, I'm gonna go back to SAP2000. And here on SAP2000, I have the default shear hinge window like you have seen many times in this video and the previous one. And you can see that the displacement normalization factor, it's not calculated automatically as a default, and it's considered as 1. So no matter what beam we have, what column or whatever what structure we have, If we use the default shear hinge in SAP2000, our yield displacement or yield strength will be 1. And coincidentally, using the value 1, we got a response quite similar to the one we expected by hand in this case. But this is just a coincidence and it might not be the case for other situations. To conclude this video, I'm just gonna go to the SAP 2000 reference manual. And here SAP 2000 indicates that we can approximate plasticity distributed over the length of an element by inserting many hinges. For example, you could insert 10 hinges at relative locations within the element, each with deformation properties based on an assumed hinge length of 1/10 the element length. So I went ahead just to see the difference that this would cause on our response. And I created the same beam, the same properties, the same shear hinges as I'm using in the other one. However, I placed many moment hinges distributed along the length of this beam. And the results here on Excel for our force displacement, it was basically the same capacity of the beam. However, our displacement got a little bit closer to what we expected by hand. Therefore, as SAP 2000 recommends in its manual, it is indeed better to use many hinges distributed along the length of the element if a distributed plasticity wants to be simulated and using elastic elements such the ones as SAP 2000. So this concludes this video. I hope you have learned a lot from what I tried to teach you or to show you in the probably past 1 hour and a half if you consider the two videos together. And I hope this helps you both in your nonlinear course as well as in your future endeavors in your career. Thank you for watching and bye bye.